Good morning, children. This is class 12 physics. We are doing chapter number 6, that is electromagnetic induction. Okay, children. So today we are going to start with the topic that is eddy current. So today we are going to see what is eddy current. We will see the reason of its production. We will see the loss due to the eddy current and how we can minimize it, plus where we can use this eddy current, right? So let's start with what is eddy current. Now children, we know that when magnetic flux linked with the coil EMF or current is induced in the coil, right? But if the magnetic flux in any solid conductor changes, then is the EMF or current induced in that solid conductor? The answer is yes. So, if magnetic flux in any conductor changes, an EMF or current is induced in the conductor. And the current that is induced in the solid conductor is called eddy current. Now, children, why the current is called eddy current? So, the reason to that is when the magnetic flux in the conductor changes, the free electrons in that conductor, children, they experience a magnetic force, and because of this magnetic force, the electrons, they start moving in the form of small loops or eddies, or in the form of whirlpool, just like the whirlpool of water. So the current that is produced due to the motion of these electrons is called the eddy current, right? So the current that is induced in a solid body due to the change in the magnetic flux is known as the eddy current, right, children? Now let's talk about the magnitude of the eddy current. Now, according to Faraday's second law, we know that the induced EMF is equals to rate of change of magnetic flux. So we can write that E equals to d phi by dt. Here d phi by dt is the rate of change of magnetic flux. Right, and children, here we know that the negative sign is in accordance with the Lenz's law. That is, it gives us the direction of the induced EMF. Now, suppose, children, the resistance of the solid is R. R is the resistance of the solid. Then according to Ohm's law, we know I equals to V upon R, right? Where V is the EMF, the voltage. So here we are writing, instead of V, we can write E, because E is the EMF, right? So E upon R, and we can replace the value of E from this equation. So your I, that is the eddy current, will be equal to minus d phi by dt upon R. And here the negative sign shows you the direction of the induced EMF. That is, it is in accordance with the Lenz's law. Okay, children. Now let's see experimentally how this eddy current is produced. So, children, here you can see in the first diagram over here. Here we have suspended a flat metallic plate. This is a metallic plate which we have suspended, means we have tied it with a thread to a rigid support. Now, what we are going to do? We are going to disturb this metal plate. So as we disturb it, it is going to get displaced from its equilibrium position, and it will start oscillating, right, children? It will start oscillating freely, and after some time it will slowly and steadily, it will come to rest. That is, it will get damped, and slowly and steadily it is going to stop, and it will come back to its equilibrium position once again. Okay, but if the same metallic plate which is suspended is kept between the two poles of the magnet, that is, we are keeping it between the magnetic field, and now if we disturb this metallic plate, then children, you will see that the vibrations, the plate will start vibrating, plate will start oscillating, but the vibrations or the oscillations of the plate, they will get damped and slowly the plate will stop. But the time in which the plate stops or it comes to its equilibrium position will be less than the previous case where there was no magnetic field. It means that magnetic field, it means that this is why, because eddy current has been developed in the vibrating plate. Let's see how, children. So children, what happens in normal position? If you see, if it is normally between the magnetic poles, right? So in normal position of rest, the magnetic flux lines which are passing through the plate, they are maximum, right? But when you displace the plate, you provide the disturbance, what will happen? The plate will start vibrating from extreme positions to equilibrium and again to extreme position, right? So when the plate is moving towards this, that is, it is moving towards the extreme position, so the magnet, it is coming out of the magnetic field, right children? So the magnetic flux that is linked with the coil, it will decrease, the number of field lines passing will decrease, right? So as there is rate of, as there is the magnetic flux is changing, eddy current is produced in this plate. And as the eddy current is produced, the eddy current which is produced, its direction will be such that it opposes the reason of its production, right? So what happens is, what is the reason of production? The reason of production is that the magnetic flux is decreasing, so the eddy current which is produced in the plate will be such that it will try to increase the magnetic flux, right? Reason of production is decrease in the magnetic flux, but the eddy current direction will be such that it will try to increase the magnetic flux. So it is going to move the plate backwards, right? Now when the plate moves backward, that is towards the extreme position this side, right? Again, the plate, as the plate is coming out of the field, the magnetic flux linked with the coil, linked with the plate, will again decrease. So again the eddy current is produced in it, which will oppose the decrease in the flux, and hence the plate will start moving towards the mean position, towards the equilibrium position. So because of the eddy current which is produced, the vibrations of the plate, they are opposed because of the eddy current, and hence they get damped very fast as compared to the previous case, right children? So this is your experimental demonstration of the production of the eddy current. Now let's talk about the children loss, that what are the loss due to the eddy current. So children, the first and the foremost loss is the eddy current. It produces unnecessary retardation. It produces unnecessary retardation. So as we saw, the metal plate, when it was kept between the between the two poles of the magnet, that is, when it was placed in magnetic field, the oscillations damped and sooner it came to rest. So what it is producing? It is producing retardation. So the metal plate, as we saw, it got damped and soon, and it stopped sooner due to the eddy current. Right. Now let's talk about the second loss. Now children, the eddy current, it produces unnecessary heat. When eddy current is produced in any metal plate, it starts heating it. Why? Due to the resistance of the metal plate. Metal plate will also have its resistance, and because of that, it starts heating up the metal plate. So the objects, so the metal objects may be damaged due to the eddy current. Okay children, so these are the very big two important losses. Now let's talk about how we can reduce it. So children, as you can see in the picture over here, eddy current, it can be reduced by making slots. Here you can see some gaps, right? By making slots or by making holes in the metal plate. Because children, if we make slots, if we make holes in the metal plates, then the eddy current will get reduced. The slots, the gap, the holes, they will cut the path of the eddy current, and so the eddy current which is produced will be less, right? One is this method. The second method, children, is by making it in the form of small metal sheets. So children, instead of using a single metal plate, we can use a number of thin metal sheets. So instead of using single sheet, you can, instead of using single plate, you can use very thin sheets together, and they are insulated from each other. So what will happen? So suppose there are very thin sheets we have connected. Let me change the color. Suppose this is red sheet, then you are having a yellow sheet, then you are having a green sheet, and then you are having a blue sheet, and then you are having a black sheet. So all these are very thin sheets, right? And in between we have provided the insulation. So children, the eddy current which is produced in one sheet, suppose in red sheet, the eddy current that is produced, it will not affect the yellow sheet. Hence the eddy current will be reduced to a large extent. Okay children, so these are the two methods how we can reduce the eddy current produced in any conductor. Now, children, it is not so that we cannot, we can use this eddy current. So, as we know, the eddy currents, they are used or they produce retardation. That is, they can stop a moving object. So, using this concept, we can use this eddy current in brakes. We can use it in children brakes. So, the electric brakes, the magnetic brakes, they are one of the place where eddy currents are used. There, large eddy current is produced which opposes the relative motion, and so the train slows down and it comes to rest quickly. Right. Next is, here you can see the induction cooker. Right. So as we know, the second loss, we saw that eddy current had produced unnecessary heat, right? So that heat that is produced, that can be used now, children. So eddy current is used in induction cooker, it is used in induction furnace. So that heating effect of eddy current is used for melting metals and induction furnaces. So eddy current of large magnitude are produced by providing, children, varying magnetic field. So as the magnetic field is changing very rapidly, so the eddy current produced will be of larger magnitude, and hence if more eddy current is produced, more heat will be produced, and that will melt a metal quickly, and similarly it will make the food faster, right children? Next is, it is used in speedometers, and last is, it is used in energy meters. So these are the applications of the eddy current. This is it children.